Okay, so I want to tell you about now strong induction. Strong induction. And I'm going to tell you about strong induction in the context of what I call representation theorems. Forget about the big word. Basically, I'm going to tell you mostly about the fundamental theorem of arithmetic. So the fundamental theorem of arithmetic. Okay. So take any number. Let's say, for example, 36. So 36 is equal to 2 times 2 times 3 times 3. Okay. And what you will observe is that this is, a natural number, okay, bigger than 2. So natural number greater than or equal to 2. And what you'll observe is that I've written it entirely as a product of primes. Okay, and that's fundamental. So it's called the fundamental theorem of arithmetic. Basically, the prime numbers are the atomic units for the integers. In other words, every integer, every natural number bigger than or equal to 2 is either a prime or it can be represented as a product of primes. It's made up of primes. Okay? And the fundamental theorem of arithmetic goes one step further and says that, once you've represented it as a product of primes, basically it's unique up to reordering. So the fundamental theorem of arithmetic basically has two parts. So part 1, every n greater or equal to 2 is either prime or a product of primes. Okay, and this is an example of writing 36 as a product of primes. And the second part is that this product of primes is unique up to reordering. So the product of primes, so the primes that appear in the product is unique, up to reordering. I mean, we don't care that you could also write it as, 3 times 2 times 2 times 3, up to reordering. Okay, this is this absolutely fundamental theorem. Fundamental. Okay. So we're going to, in some way, shape, or form, we're going to prove this theorem, and we're going to prove it in 2 steps. Okay. And today we're going to prove the first step. Okay. Later on, when we do number theory, we'll prove the second step. Okay. And to prove the first step, it's a beautiful application of induction, in particular, strong induction. Okay. So what is strong induction? So in order to sort of get to strong induction, let's see a little bit more what's going on with induction. So in induction, you prove P of 1. Okay? So you prove P of 1. So let me put it as, a check mark. Okay? And then you use P of 1 to infer P of 2 because you've proved the link P of 1 implies P of 2. Okay, so you prove the link P of 1 implies P of 2. Okay? And so you can infer P of 2. Okay? Okay? You can infer it because you proved the link P of 1 implies P of 2. Okay. Now, let's see what happens when it comes time to infer P of 3. Okay. Well, what link are we going to use? What link we're going to use is the P of 2 implies P of 3 link. Okay, so we're going to use the P of 2 implies P of 3 link. And because P of 2 is true, we can infer P of 3. Okay, so we infer P of 3. Okay. And then, what are we going to do when to get P of 4? We're going to use the link P of 3 implies P of 4. Okay, and we're going to infer P of 4. But now I want to point out something. What am I going to point out here? What I'm going to point out here is that when it is time to infer P of 4, we know at that point that 1, 2, and 3 are all true. Okay, so we don't. So this link would certainly imply P of 4. Okay, this link would certainly imply P of 4. But a weaker link would also imply P of 4. The following link would also imply P of 4. P of 1 and P of 2 and P of 3 implies P of 4. Okay? So if we have proved this link instead of this link, so the induction, or normal induction proves this link. Okay. But suppose, just imagine that instead of proving this link, we have proved this link, that P of 1, 2, and 3 implies P of 4. Would we be able to conclude P of 4? And the answer is yes. Why? Because look, we know that P of 1 is true, P of 2 is true, P of 3 is true. At the time that we come to prove P of 4, we know that all these are true, and if all of these are true, then the AND is true. If the left-hand side is true, we can infer the right-hand side. Okay. So this implication link allows us to conclude P of 4, but so does this implication link. So it suffices to prove this implication link. Okay. Now, which of these two implication links is easier to prove? Okay. It's much easier to prove this implication link. Much easier to prove. And why is that? Because let's look at the proof. Okay, to prove this implication link, we assume P of 3. Okay, and we prove P of 4. Okay, that's to prove, let's call this star. So this is star. That's how we prove star. Okay, prove star. Let's call this star star. Okay, to prove star star, okay, what do we do? Well, we're going to use, let's say we use a direct proof. We assume P of 1 and P of 2 and P of 3. So we assume P of 1, P of 2, and P of 3. And what do we have to prove? We have to prove, it's an implication, so it's a standard implication proof. We have to prove P of 4. So look at that. Okay. Over here, I get to assume P of 3 and I must prove P of 4. Over here, I get to assume more. Gives me more firepower. I get to assume P of 1, P of 2, and P of 3. Okay. And all I have to prove is the same thing, P of 4. So this must be easier to prove because I have way more firepower. Okay. All right. So, conclusion. It's much easier to prove this implication than that implication. Okay. And both of these implications will allow me to conclude P of 4. So if both of these implications would allow me to conclude P of 4, then I much rather prove the easier implication that will allow me to conclude P of 4. Okay? And that's just as valid an induction, because when we are doing the induction, it is indeed the case that everything up to that point has been proved true. Okay. So, what I'm saying, in a nutshell, is that in the induction step, so in the base case, you prove P of 1. And now I'm suggesting another induction step, which is an easier induction step, but allows us to get this infinite cascade of implications that we need. Okay? In the induction step, instead of, so before it was P of 1 implies P of n plus 1. P of n implies P of, before it was P of n implies P of n plus 1. That was the old induction step. I'm suggesting a new induction step, which is, P of 1 and P of 2 and all the way up to and P of n. So, prove a much, easier to prove implication, which is that P of 1 and 2 and 3 and 4 and all the way up to n, they're all true. Okay? You can prove that if all of these are true, then I can conclude n plus 1. Okay? And that corresponds to this logic that, and this is enough because we know that everything up to 4 is true. Okay? And since everything up to 4 is true, and we prove this implication, it means 4 is true. But then once we have 4, everything up to 5 is true. So we can conclude 5 is true. And that infinite chain of dominoes, that cascade of implications is the same as before. But now, this is much easier to prove. Induction step. Okay. Let me put this on a formal footing. Okay. On a formal footing. So I don't want to just, pull this over to you and say, here, take my word for it. Okay. So let me now prove to you that this is basically induction, but with a much stronger claim. This idea is just induction with a much stronger claim. Okay. And if I want to prove P of n, okay, let me define a much stronger claim, Q of n, which is equal to the claim that P of 1 is true and P of 2 is true and P of 3 is true and all the way to and P of n is true. Okay, let me define this much stronger claim. Why is it much stronger? Because look, this is just the claim P of n. This is making the claim that not only is P of n true, but all the way up to P of 1 is true. 1 all the way up to n is true. This is a much stronger claim. Okay. Now, let's see how we would prove Q of n by induction. So, if I prove Q of n by induction, I've certainly proved P of n, because Q of n is much stronger than P of n. So, prove Q of n by induction. Okay. How do I prove Q of n by induction? I need to have a base case. Base case. Q of 1. Okay. Which is just the claim P of 1. Which is just the claim, same as P of 1. Okay. Induction step. Assume Q of n. What do I get to assume? P of 1 and P of 2 and all the way up to and P of n. Okay. Remember, this was the idea that we just discussed, that at the time, when you come to sort of trying to infer n plus 1, P of n plus 1, you know that 1 to n are all true. So Q of n assumes that, but this is just the standard mechanics for proving Q of n. You assume Q of n. Okay. Prove Q of n plus 1. What is that? Prove that P of 1 and P of 2 and P of n and P of n plus 1 are all true. Now it's not looking like induction anymore. Okay? Didn't you just say I have to prove only P of n plus 1? Okay? It looks like I have to prove all of this, but wait a minute. Yes, you do. You have to prove all of this, but this whole left part came for free. Because you assume that 1, 2 up to n are all true. So 1, 2 up to n are all true. So P of 1, P of 2, all the way up to P of n came for free from the induction hypothesis. Okay. So the only thing you need to prove is P of n plus 1. So only need to prove P of n plus 1. Okay. And then now that justifies the method that I just described. Okay, so equivalently, strong induction. Okay, in strong induction, the base case is P of 1. P of 1, same as P of 1. So equivalently, now I'm saying this is equivalent to the base case being P of 1, and the induction step, prove P of 1 and P of 2 and all the way up to and P of n implies P of n plus 1. Okay, because we get to assume P of 1 up to P of n. Okay, technically we need to prove P of 1 up to P of n plus 1, but P of 1 up to P of n came for free, so all we have to do is prove that this implies P of n plus 1. We just need to prove that this implies P of n plus 1, and that's strong induction. Okay, this is strong induction. So, when you compare this to induction, same base case, easier implication to prove, and it basically establishes that P of n is true for all n greater or equal to 1, same as induction. In fact, it is induction. It's just induction disguised as proving a much stronger claim. Okay, and we call this stronger induction because it's proving a much stronger claim. Okay, so we're going to use induction. Actually, we're going to use strong induction, and I'll illustrate to you why we are going to need to use strong induction to prove the first part of the fundamental theorem of arithmetic. Okay, so, the idea behind induction, strong induction, all of those things is, to be able to conclude that a claim is true for a high value of n using the claim for lower values of n. Okay, so we're going to prove the first part of the theorem. So what is it saying? It's saying that every number is a product of primes. Okay, so let's see what it would take to convince you that, let's say, 2016 is a product of primes. So 2016 is a product of primes. Okay, and we're gonna sort of we're gonna use the induction approach, okay, which says, well, one way to convince you is that I show you 2016 as a product of numbers, okay, and then I have to prove to you that each of those numbers is prime. Okay, that looks relatively tough. That looks relatively tough. Okay. So, instead let's use the induction approach, which says that, my approach is going to be to somehow use the fact that the claim holds for smaller numbers to prove it for this large number. Okay. And so 2016 is equal to a product, and it may or may not be a product of primes. Okay. Well, so there are two cases. 2016 is either prime, in which case I'm done. Or 2016 is equal to a product, is what's called composite. Okay. And in this case, it turns out that 2016, if it's prime, we're done. If it's composite, then we have a problem. Because how do we know that it's a product of things that are prime? So in this case, 2016 is equal to 32 times 63. Okay, so it's a product of two numbers, any two numbers, I don't care. Okay. And this is where the idea of induction comes in. So I'm trying to prove to you that 2016 is a product of primes. Okay. If I already know that 32 and 63 are products of primes, so if this is a product of primes, and this is a product of primes, then I'm done. Okay. And I don't need to know what those primes are. I just need to know that they're products of primes. I take this product of primes, multiply by this product of primes, and I have represented 2016 as a product of primes. So 2016 is a product of primes times a product of primes, which is a product of primes. Okay, and I'm done. So easy. Okay. And now the fact that I can convince you that 2016 is a product of primes using the fact that, some smaller numbers are products of primes is an immediate hint that induction is relevant. But now here's the problem. In regular induction, I need to use the fact that 2015 is a product of primes to prove that 2016 is a product of primes. So regular induction. I need to prove that 2015 is a product of primes implies 2016. Okay, so this is analogous to the implication. So it's basically the implication. P of 2015 implies P of 2016. Okay, that's what I would need to prove. Okay, and that's very hard to prove. Okay, but strong induction, because in regular induction, I'm only allowed to assume 2015 is a product of primes in order to prove the claim for 2016. But in strong induction, I'm allowed to assume that every number below 2016 is a product of primes. In other words, the claim holds for every number below 2016. And that's when strong induction reveals its power. Because you know, in proving 2016 is a product of primes, all I need is that it's a product of some smaller numbers. And the strong induction hypothesis tells me that no matter what those smaller numbers are, and you don't even need to tell me what they are, I know that it is true that any smaller numbers are products of primes. And that's what tells us that strong induction is the right approach to use here. Okay, so let me show you the full proof in all its details. So, the claim P of n is the claim that, you know, and for n greater or equal to 2. P of n is the claim that, you know, either n is prime or n is a product of primes. Sometimes we even can ignore the fact we don't add the clause n, either n is prime, because if n is prime, it's a product of one prime. Okay, so proof. And typically we just say by induction, okay, but I'll be specific here by strong induction. So the base case is P of 2, and that's prime. So check mark. Base case is check because it's prime. Okay, now I need to prove, so this is the base case. I need to prove the induction step. I need to prove that P of 2, so prove P of 2 and P of 3 and P of 4 and P of n implies P of n plus 1. That's the standard strong induction implication. Okay? And we're allowed to make this because at the time that we need to infer n plus 1, we know that all of these are true, so we might as well assume they're true. Okay? And make that implication. Okay, so prove this implication. So assume P of 2 and P of 3 and P of 4, P of n. Okay, so what is that assumption? Okay, because I'm trying to prove an implication. What this assumption is saying is 2 is a product of primes. It's a product of one prime. 3, 4, all the way up to n. They're all products of primes. Okay. Now consider n plus 1. It's either prime, in which case you're done. Check mark. Or it's composite. In the case that it's composite, n plus 1 is equal to, let's say, m times L. Okay. And I don't need to know anything about m times L except for the fact that they are less than n plus 1 because it's composite. Okay. And these are non-trivial factors, so they're between, they're greater or equal to 2 and less equal to n. So 2 less equal to m and L less equal to n. Okay. But in that case, I got to assume that whatever they are, as long as they're between 2 and n, they are products of primes. So this is a product of primes, and m is a product of primes, and L is a product of primes. And so that means that n plus 1 is a product of primes. You just take this product, multiply by that product, you get one bigger product of primes. Okay? And so I proved this implication, and that's the strong induction mechanics. So, therefore, we have proved that P of n plus 1 is true. Okay? And so by induction, P of n is true for all n greater or equal to 2. End of proof. We have proved the fundamental theorem of arithmetic part 1. We have proved that any number greater or equal to 2 is a product of primes. The primes are the atomic units for the numbers. Okay. Later on, we'll prove that that product is unique up to reordering. Let's do another example with strong induction. By the way, this fundamental theorem of arithmetic is called a representation theorem, because what does it do? It represents the integers using some other object. Okay. So it says that any integer greater than or equal to 2 can be represented as a product of primes. Okay, I'll end today's lecture with, I'm just going to give you 2 exercises. Okay, and you can solve both of these exercises using strong induction. So just to show you the variety, the amazing variety of applications of strong induction. And if you're having difficulty solving these problems, well, it's all in the book, in chapter 6. And I'll probably make a supplementary video on these 2 problems for those of you who are interested. Okay, so problem 1. Problem 1. Binary expansion. Binary expansion. Okay, so you have probably all seen binary expansions. Okay, so let me give you an example. For example, 18 is equal to, 2 to the 4 plus 2 to the 1. Okay, and so that has the binary expansion 1, 0, 0, 1, 0. So this is the 2 to the 0 place, this is the 2 to the 1 place, this is the 2 to the 2 place, this is the 2 to the 3, this is the 2 to the 4. And so what this compact notation, okay, is, it's saying 0 times 2 to the 0 plus 1 times 2 to the 1, that's that term, plus 0 times 2 to the 2, plus 0 times 2 to the 3, plus 1 times 2 to the 4, that's that term. Okay, and so we call this the binary representation of 18, or some of you might say 18 in binary. 18 in binary. Okay, and it may never have. You may have taken this as obvious, but what is a binary representation? Is it's exactly a representation of a number as a sum of distinct powers of 2. So we represent n as a sum. So represent, and hence it's called a representation. So you represent n as a sum of distinct powers of 2. Okay, interesting. And where the coefficients are either 0 or 1. Okay, so it's in this case it's 0 times 2 to the 0 plus 1 times 2 to the 1 plus 1 times 2 to the 4. Okay, and you might have taken this for granted, but an interesting question arises: can every number n be represented in this way? So theorem, and just like the fundamental theorem of arithmetic, which is another example of a representation theorem in terms of primes, theorem, every n can be represented as a sum of distinct powers of 2. In fact, it can be represented in this way uniquely. So there's no other way to represent 18 as a sum of distinct powers of 2. That's also interesting. Okay, so just like the fundamental theorem of arithmetic, this says that the representation exists for every n, and it's also unique. Well, you can think about, you took this binary representation for granted, but how do you prove that you can always find a binary representation for a number? Okay, so proof. Try to prove this by strong induction. And if you're having difficulty, it's in the text, and I'll probably make a supplementary video about this problem. It's too much to include in the lecture. We only have a finite time in the lecture. Okay, so read the text, or maybe watch the supplementary video if you're interested. Next, application of strong induction. So there's this, strong induction is very useful for, and induction in general is useful for analyzing, algorithms, recursive, greedy, dynamic programming. It's also it's also very powerful for analyzing games, especially strategic games. Okay, so there's a game called NIM, which means to steal or to pilfer. Okay? And I'm going to show you a very, very, very simplified version of NIM where you have two piles of coins, so pile 1 and pile 2. Two piles of coins, 1, 2, let's say here I've got 5 coins, and here I've got 5 coins. So we're considering the case where the piles are equal, okay? And at each turn, so you have two players, you have player 1 and player 2, and you take turns picking a pile and taking any number of coins from that pile. So if player 1 picks all the coins from pile 1, okay, so if player 1 picks all these coins, well, then player 1 immediately loses because player 2 will pick all the coins from the other pile, and the winner is the player who is the last to move, is the last to be able to take coins. So you win if you take the last coin. Okay, so clearly player 1 taking, all the coins from one pile at his first turn is going to be an immediate loss. Okay, so player 1 is not going to take all the coins. Okay, maybe he'll take 2. And now player 1 comes and takes 2, and now player 2 comes and has to decide how many coins to take and from which pile. So what will she do? Okay, so there's an interesting strategy which is called the equalization strategy for player 2. So if she equalizes the piles, okay, i.e. whatever player 1 does, she does the same thing to the other pile. So the equalization strategy. So player 2 does the same thing player 1 did, but to the other pile. So in this case, so player 1 took from pile 1, so and took 2 coins, so player 2 takes 2 coins from pile 1. 2 coins from pile 1. Okay, that's called the equalization strategy. Okay, and you see why it's called the equalization strategy, because it renders the piles equal again. Well, it turns out that this equalization strategy will guarantee that player 2 can win. So, player 2 must win. No matter how many coins are in the 2 piles to start with. Okay, so I've just given you a strategy and I'm claiming that player 2 must win. Okay, but how do we know that? How do we prove that? You can use strong induction to prove that. Okay, so just to show you the range of applications of induction. Representation theorems, analyzing games of strategy. We'll see it in analyzing recursions, greedy algorithms, dynamic programming. Wow! Induction. Get to know it early. Signing off.